start. So thank you all for coming this tutorial. So I'm Wei Zhang, and I'm going to introduce the general object detection with MMDetection. So what is object detection? So the traditional meaning of object detection aims to predict a set of bounding boxes of things. And in a more general meaning, in recent years, it also includes like instant segmentation, which predict a set of bounding boxes and masks of things. Also, it can be panoptic segmentation, which further predict a set of masks of both things and stuff. So the challenge of object detection includes that it contains you need to output variable numbers of objects per image. Also, it needs to predict what and where in the image. It will also face occlusions and many small objects in the image. So to handle these challenges, classic methods adopts a sliding windows mechanism, which use, for example, like the fast-RCN, it will use go through the each potential position of the dense feature map, and finally produce a sparse set of region proposals. And then for each proposal, it will predict regional features for each proposal and use it for the final classification and the bounding box regression. And to extend this framework for instant segmentation, you only need to simply add in a convolutional branch in the fast RCN, which is the mask RCN, achieves a better good speed and accuracy trade-off for instant segmentation. Also, the whole image feature representation can further be improved by multi-scale, because we know that there are many small objects in the scene. So we could use the multi-scale features and go through the region proposals at each scale of features, so that we could recall more small objects. Such a paradigm named feature pyramid network are also adopted in the panoptic segmentation. So in panoptic FPN, it also adds a semantic segmentation branch based on the mask RCN framework, which further extended the FPN for the panoptic segmentation. We know that in the real-world applications, the two-stage method faces many deployment issues, like because there are two small networks in the whole framework, and we need to handle the ROI line. So in real-world applications, the community prefers one-stage object detectors. However, in one-stage detection, we face more issues, especially the imbalance between the positive and negative samples, because we want to just simply go through the whole feature pyramid networks, and we want to predict accurate boxes. So focal loss is proposed in the RetinaNet. Basically, it will put more loss weights to the hard examples. This loss also becomes a default and a common technique in many following one-stage object detectors. And the later improvements also adopt anchor-free object detection, which further through the anchors away and use points as a representation to represent objects, and further simplify the detection paradigm. So in 2020, detection transformers are proposed to further simplify the detection paradigm, and it take a very big step to unify the vision modeling with the language modeling. So basically, it represents the objects and pixel groups by a group of queries. After taking the vision features, it uses a transformer encoder, and it uses a transformer decoder to decode a set of queries and do the final box prediction and classification. Such ideas are also adopted for the segmentation tasks. Then later works like mask-former, mask-2-former, and KNet, they start to segment the things and the stuff unanimously by a group of dynamic kernels or mask embeddings. Take a further step based on the detection transformer. We know that in language modeling, basically it adopts a sequential modeling for the words. So to further unify the vision frameworks and unify different kind of visual tasks. So the Pixel 2 sequence takes a step which forms the object detection paradigm as to predict a set of location tokens. And in Pixel 2 sequence V2, it unifies the detection, segmentation, and then key point estimation with the caption task. So it unifies the location prediction and the language walls in a unified vocabulary so that we could use a unified decoder to decode either the bounding box positions or the language words. More recent work named Vision LLM take a further step. So basically, the Pixel 2 sequence is decoder is very simple and inspired by the recent advances of the large language model. We could further combine the vision models with the large language model and use the large language model to predict more than words, but also the positions or other desired outputs for vision tasks. This is also a further step that unifies the visual prediction and the language modeling. And another foundation model I would like to introduce for the detection and segmentation is the segment anything model as introduced in the previous tutorial. So basically it adopts an image encoder and a lightweight mask decoder to predict the mask. So the most important knowledge we could learn from the segment anything is that the data quality and the data loop. So basically it adopts the model to annotate the data and then it uses the annotated data to train the model so that the data set could gradually grows in a large scale. And due to the large scale data, the SAM becomes a new foundation model and has been used in many directions. For example, in the 3D segmentation, we could use SAM to distill its knowledge for the 3D segmentation. So in ML detection, basically we have already supported many object detectors since the first RCN in 2014. And now, till now, we already support like many two-stage detectors, single-stage detectors, and many detection transformers, including the state-of-the-art one-stage detector RTM-DET, and also the most recent transformer detection transformer like CoDTR and DDQ. So how ML detection supports so many object detectors? So basically we adopt a very flexible modular design. For conventional detectors like the one-stage and two-stage detector, and we adopt a design shown in the right figure. So basically, it decomposes the object detector into the data preprocessor, backbone, and the neck. So the neck, like the FPN or NAS FPN, they extract multi-scale features and send them to the dense head. So basically, for one-stage detectors, it will answer the dense head. It will go through each position and predict a set of bounding boxes. And in MMDetection3, we allows our one-stage detector becomes a region proposal network. So basically, after predicting a set of objects, we could send these bounding boxes to the ROI head to do the further refinement, so as did in the first RCN. So we could use the ROI extractor to extract the features and use the box head and the mask head to predict boxes and instance masks. So this is basically a simple modular design and is universal for all the one-stage and two-stage detectors supported in MMDet. Also, for the most recent detection transformers, we adopt a little encapsulation for supporting different kinds of detection transformers. So basically, it will also take the features extracted by the neck, and then a transformer encoder and a transformer decoder will be will extract the features, and the decoder will also take the queries and use the queries to predict and send them to the detection DTR head, and the DTR head will do the bounding box prediction and the mask prediction. So such design also allows many explorations based on the detection transformers, like different distillation methods, or exploring different kinds of auxiliary losses, or the different kinds of supervision signals, like those implemented in the co-DTR or DNDTR. So in 2023, basically MMDetection has these 4 features. It has already covered all the detection transformers as introduced in previous slides. And it also supports rich backbone networks from the ResNet to the most recent connects to V1 and V2, so as all the backbones in MM class and TIMM. Also, it supports abundant general plugins like the deformable attention in the deformable DTR. It also supports many sufficient training techniques, including strong data augmentations like auto augmentation and simple copy paste. These techniques can also be used for the semi-supervised pipeline, and so as the software teacher is supported in MMDet. We in the past few months, we also support DATIC, so which means that we support open vocabulary object detection, and we allow multi-dataset training for the open vocabulary object detection. MMDetection also has a thorough support for model deployment. So basically, there are more than 18 algorithms in MMDetection supported by MMDeploy, and they can be exported to more than 5 backends. And basically, this support covers many common object detectors and the instance segmentation models. Nowadays, MMDetection has already served as a foundation of detection-related libraries in OpenMMLab. So as you can see that in the bottom, MMDetection3 serves as a platform which supports many libraries which take MMDetection as a core library, which is also detection-related libraries like MMDetection3D for the 3D object detection, and MMRotate, MMOCR, and the MMEuro targeted for the industrial applications. Also, there are many other libraries like MMTracking and MMPose. They take MMDet as a dependency. So just to take several examples that based on MMDetection for introduction. So I would like to introduce MMDetection3D, which is the most comprehensive and popular library for 3D perception. So now it supports the indoor and outdoor point cloud-based 3D object detection. And it also supports 3D object detection based on different kinds of modalities, like the image-based 3D object detection and multi-modality 3D object detection. It also supports different kinds of segmentation methods for outdoor or indoor point cloud segmentation. Also, I would like to introduce MMEuro. So basically, it is a new open source library targeting on the industrial applications, which has faster training speed and more comprehensive documentations for the industrial applications than the MMDetection. So it also supports multitask models based on the MMDetection, MMRotate, and MMPose. So basically in MMEuro, we support most commonly used one-stage detectors like Euro V5 and Euro X. We also develop a faster and more accurate detector named RTMDet. It is also based on the OpenMM 2.0 version. So it relies on MM Engine and MMCV and MMDetection, so as the MMDeploy. Also, I will there have been several years since the first RCN, and you may ask that what's the new trend or new issues that to be solved in the object detection field. So here are two examples explored in MM detection. So the first one is the occluded object detection benchmark, which is developed by the VGG team. And this benchmark has already been supported in MMDetection3. So basically, it uses a scalable way to generate the evaluation data set for evaluating the detection capabilities in two conditions. The first condition is the occluded COCO, which aims to detect the objects under common occlusions. And in the severe occlusions, like the objects are separated in the image, it also evaluates this condition named the separated COCO. And it provides a data set for these two conditions, and including annotated this so many objects. So occlusion is a new challenge scenarios for the object detectors to explore and to conquer. Another new trend I would like to introduce is the open vocabulary dense prediction, or specifically we could use open vocabulary object detection. So open vocabulary dense prediction tasks that aims to detect objects of categories not seen or we so-called not fully annotated during training, which means that there are always some objects that that we do not have their bounding boxes in our training, and but in real world applications, we need objects to detect them. So open vocabulary is a very big step from the traditional object detection to the general object detection, so as the general machine intelligence. So behind the open vocabulary object detection, it needs some basic techniques. The most common one is multi-data set training. Usually or intuitively, if we include more training data set, so as the visual grounding data set or the image data set, we could have more data, then the model could generalize to more unseen scenarios. So this is what the GLIP and DATIC done in their works. Also, we could use weak supervisions. So the bounding box annotations, they are very expensive, but the image labels are cheap. So in DATIC, we could use image classification data set and adopt it for the object detection. So in the most recent MM detection, we already support the DATIC, which including both the training and the testing. Also, the MMDetection team support GLIP with better accuracy than the official implementation. The GLIP will be released in the next few months. And here is an example about the traditional detection and the DATIC implemented in MDet. So traditionally, we also only train the models in a finite set or a predefined vocabulary provided by the training data. So this is the detect objects in the LLM-based vocabulary. After the DATIC training supported by MMDet, we could see that the detectors, if we let the detectors to detect a headphone or webcam, a paper, coffee, and the detector could follow all instruction and successfully detect related things. As you can see that the headphones, originally they are earphones specified in the LVs, and so as the paper. And in previously, they are called newspapers in the LV's vocabulary. So the open vocabulary makes the object detection more applicable for the real-world applications. The third new trend I would like to introduce is about the trend with large language models. So as you guys may notice, the recent advances of the ChatGPT, Bard, and GPT-4. So OpenMMLab also starts to think about that. What can we do if we have rich AI models in the era of the large models? So one very obvious issues we can know that is large language models, they only accept text as input. However, our world is multimodal. So all the rich AI models in OpenMMLab, they basically provide the multimodality understandings of the visual world or multimodality world. So basically, all these models can serve as extensions to make the LLM see or understand the visual model. So this essentially turns a large language model to a multimodal agent if we incorporate the AI models with the language model. And this is also explored in the CVPR 2023 best paper visual programming. And so although this repository has not been released, we just cannot wait to share this repository with you. So basically, we developed a project named Agent Lego. Basically, the Agent Lego provides a multitask and multimodality AI toolset, including object detection, segmentation, and the post-estimation models. So these models are all supported in OpenMMLab. They are lightweight and efficient and accurate. Also, we support tools like translation and speech recognition, which are also useful tools for the language model in the real-world applications. And the Agent Lego provides an extensible tool interface so that it could be flexibly adapted to different agents supported in the Lagent and the Lagent, which will be introduced later, and the transformers agent. It also provides the tool search and serving. So basically, Agent Lego connects the large language model to other AI research fields, and it augments the language model by AI tools of other modalities and tasks. Here are several demos. So basically, with the large language model incorporated with Agent Lego, we could upload an image and ask the model where is the dog, and the language model could call the object detectors implemented in MMDetection and return the bounding boundaries of the dog. Also, it could also use the text-to-speech tools, and it could return voice to us. And it also there are VQA models in the Agent Lego and the text-to-image models, which could turn all text inputs into an image. So how to use the model tools in Agent Lego with the large language models? Basically, we could use Agent Lego with internal LLM, large language model toolchain. So basically, such a toolchain includes the training tools for training the internal LLM or fine-tuning the models. It also provides the deployment tools like MMDetection, so that we could deploy the model and chat with the model in a faster way. And based on the MMDetection, we could use the Lagent, which is an agent framework that could turn a large language model to a language agent, so that it could call the tools in the toolset provided by the Agent Lego. So what is Lagent? So basically, we developed Lagent because we have already observed many limitations of large language models. We know that it cannot do the numerical calculations well when the number is very large, or it cannot catch up with the most recent informations or news happened every day, or the language model cannot guarantee the truthfulness of its answers. And also it cannot perceive the visual world or the multimodality data. So all these issues can be reduced or solved by a simple way, is to use external tools to augment the language models. So in Lagent, we implement a general agent framework by adopting the design shown as the right figure. So although this agent framework it doesn't support memory for now, and we will support memory in a few months. So basically, the LLM could take the human instructions or the observations in the text formats as input, and then based on the inputs, it will do some kinds of reasoning or task planning by different kinds of planning mechanisms listed as plan, act, iteration, or plan then act, or reflection. So basically, the green boxes indicates different kinds of plan and action mechanisms implemented by different kinds of algorithms. And then after reasoning, the model could do some action, and the action will be sent to the action executor, and the action executor will eventually call the external tools like Python executor, search engine, or the calculator, and return the execution results to the LLM. So with the external tools, the LLM could do the calculation or answer the news in a better way. So so the Lagent basically it provides a general tool calling framework. It supports different tool calling format. So the first one is the most classic method named the reasoning and act, also called the React. So it takes the text inputs, and the model will choose a tool, and then it will make a decision to take action. And it will also check whether the task is complete. If it is not, it will further choose a tool to finish the remaining steps, or it can simply decide to end the loop. So besides the React, we also have some framework called Review, which including decompose and planning, and do the action in a directed action graph. So also the famous AutoGPT, it includes the human intervention in the execution loop. So Lagent also supports many different kinds calling format. Also, it supports different kinds of models, including the closed source models like GPT-4 and GPT 3.5. It also supports many open source models, including the Llama and the InterLM, and all these transformers supported in the Hugging Face transformers. It also supports many tools like the AI tools supported in Agent Lego, or the search or calculator tools. We call it like capability extensions supported in Lagent. It also can call thousands of rapid APIs. These APIs are already supported in the Toolbench. So when combined with the LLM 20 billion model, as introduced in the previous tutorial, we could train it as a language agents, and you could achieve a new state of results on the Toolbench. So basically, Toolbench or the tool eval leaderboard evaluates the model's capability to calling thousands of rapid APIs from the financial, sports, or the news, or different kinds of fields. And as you can see that in the leaderboard, basically the LLM 20 billion model, it achieves more than 16% win rate in comparison with the ChatGPT. So in the tool eval leaderboard, the LLM 20 billion can achieve a state-of-the-art results with the Legends. And here is also a demo when we use LLM 20 billion model with the Lagent and use the tools implemented in Agent on Lego. Basically, we have a web demo, as you can see, and if we send an image to the model and let it to describe the image and save it to audio, we could see that the models will take 3 steps. The first step is that it will do the image description. Basically, it will think that I need to use the image description and text reader API, and then it will call the image description, and then the system will return the execution results named a puppy and a cat sitting on a blanket. And then the model will reasoning the next step. So it will think like, okay, now that I have the description of the image and I need to use the text reader API to save it to audios, then it will call the text reader and convert the text to audio. And the finish action will decide that, okay, I have already finished all the instructions and I can return the final answer. So how it achieves behind these agent systems, this is, I will later introduce the implementation details of the React and the function call. So basically, there are three roles are chatting in the agent system. So the first is the system. Basically, it is the overall driver, which provides functions and the process definition and call the functions and returns the function results to the model. So basically, this is defined by us. And the human is the users who provide instructions or some feedbacks to the model. And the bot is the language model that can plan, reason, and act, and summarize the final outcome. So basically, the language model act as a bot in this role, and it will do the predictions. And the system is defined, and the human will send the instructions in our daily usage. So when we launch the whole system, the first step is to do the system definition. So basically, there is a role named system will send the messages to the bot. And at every session, the language model will receive a message like this. It tells the language model that you are a smart AI assistant, that you can use external tools, and there are several available tools. And it will provide a protocol to let the language models to know that if it want to call some model, it should output the sort action arguments. So this is the format protocol between the system and the model. And the observation and the final answer is also a kind of format that the system or the model will follow. And then in the second step, if we upload an image and ask the question, please describe the image and save the audio. So basically, it becomes the human input, and this description will be sent to the model, and we will also tell the model the image path of the image, and then the model will do the reasoning and take the action. So it will output the following texts following the instruction format specified by the system. So basically, it will first think, okay, I need to use the image description, and I need to also call the text reader, and then it will take the first action, which is to call the image description and send the image path as the action or the function arguments. And then the system will call the function and return, and will pass the model's outputs and extract the sort action arguments and execute the function with the arguments. And so it will return that the execution result is a puppy and a cat sitting on a blanket. And then in the fifth step, so basically the bot received all the previous messages and then it decided that, okay, so I have the description of the image, and I need to use the text reader API. So it takes a second action to call the text reader and send the text to the functions. And then the system will execute the step 4 to call the function and return the observations. And finally, the models know that it has already got all the answers it needs. So it will do the summarization step. It will return the final answer to the user and tell that the voice audio has been saved in a link. Okay, so basically that's all the whole process of the Lagent with the agent Lego, how the models call the different AI tools to finish the multimodality tasks working as the multimodality agents. And you may, if you are interested, you could scan the QR code to start or issue the Lagent projects to know more about of Lagent. That's all for this tutorial, and thanks for your listening. Yeah.